Hello and welcome to our physical sciences session. My name is Temba Ncube. Today we are focusing our attention on calculations on acids and bases in the context of reactions. We'll look at also some of the very important aspects of a titration. Right now, let's look at some of the the most important concepts that we shall discuss for today. So in as far as the concept map is concerned, we know that acid-base reactions are also represented in the form of chemical equations now, but in these chemical reactions, they will be taking place in the context of a titration, right? Okay, now let's look at some of the very key terms that we would use for the purpose of today's session, and some of the stuff that we already know that we need to remind ourselves of. We shall talk about concentration of solutions. So this is the concentration of a solution, right? Because most of these reactions, they take place in aqueous solutions. And then we'll talk about a standard solution in the context of concentration. We'll also look at the pH of a solution and also chemical indicators in the reactions involving acids and bases. Right. Now, let's look at the first concept that has to do with the acids and bases, but it's something that we already know. When we talk of concentration of a solution, it actually gives us an indication of the moles of a solute in a given volume of solution. So this solution is actually a homogeneous solution, right? It's actually a homogeneous solution, meaning that the solute is completely soluble in the solvent. So a concentration of a substance gives us the moles of substance per unit volume of a solution. So that's the SI unit. So remember, when we talk about a cubic decimeter as a volume, okay, right, we are talking about a liter, okay, of a substance, okay? And then also, we know that if we calculate concentration of a substance, we use the formula concentration is moles of substance per unit volume of solution, which is something that we need to familiarize ourselves as far as the data sheet is concerned, right? Okay, now, very, very important, we'll talk a lot about the standard solution. And at a later stage, we'll also discuss how exactly a standard solution is made using, some of the common substances that would subsequently use in the reaction between an acid and a base. Right, so what is a standard solution? A standard solution is a solution whose concentration is known exactly. Let's say, for argument's sake, we've got a solution of sodium hydroxide, right? Remember, it's a homogeneous solution. Now, we are saying that if, for argument's sake, there is a concentration of 0.2 moles per cubic decimeter, what does that tell us? It tells us that the quantity of the solute, okay, because C is equals to moles per unit volume. We are saying that if the concentration is 0.2 moles per cubic decimeter, we are saying that there is 0.2 mole, okay, per unit volume for every cubic decimeter. So a unit volume in this case, it's a liter or a cubic decimeter. How about if we talk about 0.5 molar? So the term molar would represent mole per cubic decimeter. So these two units, molar and mole per cubic decimeter, it represents one and the same thing in the context of concentration, right? So for the other one, it will be 0.5 mole, okay, that's the quantity of solute for every cubic decimeter. So this is what it means when we talk of a solution that is a known concentration. Right. Now, how exactly do we prepare a standard solution? Okay. Now, a standard solution, remember, it's always a homogeneous solution. So the substance that the solute must be completely soluble. Okay. So it should be a pure substance. Remember, a pure substance is an element or a compound that is highly or completely soluble. Okay. So we need to determine the mass of that sample of solid correctly. Why do we need the mass? We know that for us to actually talk about the quantity of substance, we always refer to the mole. because a mole of any substance contains the same number of particles, right? So it's always the SI unit, which is the mole. So if we've got the mass, we are able to determine the moles of that substance present in a sample, right? So the moles of substance is mass of sample that will weigh in the sense of us obtaining the mass, so that there's a scale of measurement that comes in there. So it's mass over molar mass. So if we've got the mass of sample, we are able to determine the moles of substance, okay? Then after that, we can transfer the weight solute into a volumetric flask. A volumetric flask would give us, you know, a fixed volume of a solution. And if you talk of a volumetric flask, this is how it looks like, okay? So it's got a measuring line. In this case, this is, say for argument's sake, a 250 mil, okay? That's the volume. So where there is a measuring line there, that's the amount of water or distilled water that we put into the measuring flask. And then it's got a stem, and then remember the mils for every cubic decimeter, right? There is 1,000 milliliters. Okay, so this is like a quarter of a milliliter. So if we know the moles of substance and we know the volume of solution, we are able to determine the concentration of that substance. As a result, we can say, okay, this is the concentration of the solution, right? Okay, now, furthermore, we will add a small amount of distilled water. This should be pure water, okay? It's not contaminated. And then the swelling part actually says to us that we want to dissolve it completely. Remember, we want to form a homogeneous solution. And then we add more distilled water until the bulb is up to 75% full, okay? Then we make sure that there are bubbles, the bubbles are taken out so that it's actually an accurate, you know, solution. Hence, we're saying it's a standard solution, right? Okay, then when we carefully add the distilled water till the water level, okay, it will rise up the stem, as you'd have seen in exactly how, you know, the flask looks like. And then when you take measurements, make sure that you take it below the meniscus. So the meniscus is actually the curved part of the liquid. So on the stem, so on the surface, it will be like this. So the meniscus is that curved part. So this is actually the reading that we take. It could be 250 mils as it was in that example. So this has to do with the accuracy of taking readings, right? Okay, right. And then we can also try to understand what exactly the concentration of a solution tells us, okay? Let's say, for argument's sake, we've got a solution of sulfuric acid with a concentration of 0.5 moles per cubic decimeter. So remember, this is an aqueous solution. So water is the common solvent in which these homogeneous solutions are found. Now, if this is the concentration of the acid, which is 0.5 mole per cubic decimeter, okay? Now, remember, this acid, what it does is, in the presence of water molecules, there are two ions that make up that substance, the sulfate and the hydrogen ion. So for every mole of sulfuric acid, there is double the number of moles of the hydrogen. So, and again, for every mole of the sulfuric acid, there is the same number of moles of the sulfate ions. So, which is why that when this acid ionizes, what happens is the concentration of the sulfate ion will be the same as that of the sulfuric acid because of the stoichiometric ratio 1:1, right? Why is it that the concentration of the H plus ions is double that? It's because the ratio is for every mole of sulfuric acid, there is double the number of moles of the hydrogen ions, which is why the ratio is 1:2. So this is what exactly concentration of a solution tells us in as far as the standard solution, right? So we've already looked at these formulae and how they come together in terms of calculating the concentration, okay? So at the end of the day, if you've got the mass and the volume of solution, you are able to determine the concentration, you know, practically, right? Okay, now, just as an example, we've got 5 grams of sodium hydroxide, which is dissolved in 500 cubic centimeters, okay, of distilled water. Determine the concentration of the solution, right? Now, if you look at this example, what it says to us is that for us to determine the concentration, we need to say, okay, how many moles of substance are there, okay, divided by the mass multiplied by the volume, all right? So first things first, we need to determine from the periodic table the molar mass of sodium hydroxide, okay? So we know that the moles of this substance is actually, we'll say moles is equals to, actually this is the mass, okay? The moles is equals to mass over molar mass. So this formula, what it essentially does, it takes into account the fact that we would already have determined the moles. So we would say then C, which is the concentration, mass of sample is 5 grams, okay, divided by the molar mass of sodium hydroxide. Sodium is 23 plus 16 plus 1. That gives us a 40 grams per mole. Then what is the volume? But remember, the volume needs to be in cubic decimeters, which is the SI unit. So this would be like 500 divided by 1,000, which is 500 multiplied by 10 exponent negative 3. So it will give us a concentration. Then if we go to our calculator, okay, we would have, just to get that value, 5 divided by 40 multiplied by 500 multiplied by 10 exponent negative 3. Okay, that's the same as dividing by 1,000. Okay, so the concentration of this standard solution is 0.25 moles per cubic decimeter. Okay, 0.25 mole per cubic decimeter. Okay, so that's exactly how we determine the concentration of this solution. So if we say this is a standard solution, it says that its concentration is known, and that's exactly how we actually go about that. So that's as far as, determining, the concentration of a standard solution or making a standard solution so that the concentration is known. We shall look at more examples after the short break. Let's take a short break for now. Welcome back. We're still looking at calculations that have to do with the reactions of acids and bases. But also what is important, we also want to understand some of the aspects that are important in as far as what exactly happens when acids and bases react with each other in the context of titrations. Okay, there's the whole issues around the indicators, the neutralization reactions. Now let's focus our attention on some of those aspects for now, right? We are saying that terminology forms a very important part of our understanding, because basically that is actually the language that we use. So let's be mindful of the following terms. Maybe you also need to familiarize yourself. That's pH, that has to do with the pH scale. You would have been exposed to this, previously. We also talk about chemical indicators, that have to do with color change when an acid-base reaction does take place, in the context of a titration. So it's all about acids and bases reaction, and then the titration as a technique, right? Okay. Now, the pH scale, okay, of a solution actually is an indication or a measure of the concentration of the hydrogen ions in a solution. So you'd familiarize yourself with the equation pH is equals to negative log of the hydronium ion concentration, all right? So this is in the data sheet, but we're not going to focus our attention a lot on the actual calculations. But let's also be mindful that it's about the concentration of the hydronium or the hydrogen ions in a solution. And also the scale, which ranges from 0 to 14. So anything between 0 and less than 7 is actually acidic, right? and then 7 is the neutral measure of a solution or a substance, and then beyond 7 to 14, it's a basic solution. So, acidity of a substance increases from your left, so from 7 to 0. So a substance whose pH is closer to 0 is a stronger acid, while a substance whose pH value is closer to 14 is a stronger base. Okay, it's more basic. So while 7 is neutral. So that's our pH scale, right? And then indicators are very important in the sense that in these reactions between acids and bases, at some point or the other, when we do the titration, as we'll go through the actual procedure involved, when a titration is conducted, we need to get an indication when the reaction, between an acid and base has reached some sort of neutralization, a pH value which is closer to 7. So we've got different substances that we can use as indicators depending on the types of substances or acids and bases involved in that, acid-base reaction. Okay, so these chemical indicators, they actually color change is more qualitative. So the color change, which is something that can be observed, is what is important in as far as the use of indicators in acid-base reactions. Okay, so there are different types of them. Okay, we've got bromothiamol blue, whose color change is between pH 7 and 8.8. Okay. This is actually the one that we choose for argument's sake if you are reacting a strong acid and a strong base. We'll talk about strength at a later stage. Okay, there's also phenolphthalein between 8.3 and 10. Those are the pH values. We also have methyl red as well as methyl orange. So our choice of an indicator entirely depends on the type of acids and base involved in that chemical reaction, right? And then basically, as part of pre-knowledge, we understand that when you react an acid and a base, it's typically a neutralization reaction, in most cases. But generally, if an acid and a base react with each other, they actually form salt and water, okay? So that's the general equation involving an acid and any base for that matter, okay? So it's a neutralization reaction. Okay, this is with respect to the changes in pH. Okay, so this has to do with pH change when this reaction between an acid and a base occurs. Okay, we also know that acids have got high concentration of hydrogen ions. Okay, but this is the assumption that these are actually strong acids. At the back of our mind, we will talk about strength of acid at a later stage, but we assume that any acid will ionize to give us H plus ion, while bases, they give us the OH minus ion, okay, which is the hydroxide, okay, right. And then a titration becomes then a technique, right. So it's a procedure that is used to determine the neutralization point of an acid-base reaction. So for you to determine the neutralization point, we make use of the indicator in a reaction between an acid and a base, right? So hence we're saying that generally or ordinarily, this is actually a neutralization type of a reaction if we were to classify these reactions as we know them, all right? Okay, furthermore, we know that we must be reminded that in a titration, there is an observed color change, okay, of an indicator. The color change is only possible once in the reaction between an acid and base, we've added in a suitable indicator. So at the time when there's a color change, we've reached what is called the end point of a titration. So end point is another key term in as far as acid-base reactions are concerned, right? So at the end point, what exactly happens? All the reactants have changed into products. And when a reaction, all the reactants have changed into products, we've actually reached what we think of as completion of a reaction, okay? This is also described as the equivalence point or the point of equivalence. So these are some of the, important aspects of a typical acid-base reaction that we need to be mindful of, okay? So ordinarily, a titration is used to determine the unknown concentration of an acid or a base. Now, earlier on we spoke about a solution whose concentration is known. Now we are saying that we use this technique of titration to actually determine, the unknown concentration of a solution. So there are two things here that come out very clearly, that as a technique in a titration, what happens? You use a standard solution whose concentration is known to actually determine the concentration of another solution which we do not know. Okay? So it's from known to unknown. That's basically the long and short of what the technique of titration actually involves, right? So this type of calculation involved in a titration. So the titration is the technique. The stoichiometric calculation would describe them or refer to them as volumetric analysis. So if we talk about volumetric analysis in titration, is that we carry out a titration, and then subsequent to that, we do calculations which are described as volumetric analysis to determine a known concentration using a standard solution. Basically, that's what it means, right? Okay, and then if we can quickly just reflect on a few things that are very important. The end point of a titration, all the substances have reacted, okay? So we have got the maximum amount of products, which is salt and water. But the indication that this has happened, we achieve it by an indicator, which gives us a color change. So this is the most important part of the titration, to say, when do we stop adding one substance to the other so that the reaction does take place? When there is a color change in the indicator, then the substance is actually, then the reaction is actually reached equivalence point. Okay, so an indicator, qualitatively, I think that's exactly its role in as far as the titration is concerned, right? So volumetric analysis, that's another term that we also touched on. So the calculations involving concentration, the moles of substance, determining the unknown concentration, all those, mathematical calculations that follow would refer to them as volumetric analysis, right? So the follow-up question as to determine the concentration of the hydroxide ions in the solution. So now we are saying that this sodium hydroxide has a known concentration of 0.25 moles per cubic decimeter. So concentration, of sodium hydroxide, right? This aqueous solution is equals to 0.25 mole per cubic decimeter, right? It's a standard solution, right? Now, when this sodium hydroxide solution in that homogeneous solution actually dissociates completely, we have something of this sort. We have got the sodium ions, okay, right, as well as the hydroxide ions, right? Now, this question demands us that we determine the concentration of the hydroxide ions in the solution, right? Remember, this is an aqueous solution, so the stoichiometric ratio for this dissociation or the breaking down of this ionic substance is actually 1 mole of sodium hydroxide gives us a mole of the sodium ion as well as a mole of the hydroxide ion. So the ratio is 1:1:1. So if the concentration of sodium hydroxide is actually 0.25, okay, mole per cubic decimeter, the concentration of the sodium ion will also be, because of the ratio 1:1, will be 0.25 mole per cubic decimeter. Then what about that of the hydroxide ion? Because for every mole of sodium hydroxide in that solution, there is a mole of the hydroxide ion. So the ratio still remains 1:1. So this gives us 0.25, okay, mole per cubic decimeter. So this is what it means. If it's a standard solution and there's complete dissociation of sodium hydroxide, a mole of sodium hydroxide gives us a mole of the hydroxide ion. So in other words, this is the concentration that the question actually requires us to determine. But in determining it, we also used the balanced equation of that, dissociation or the breaking down of that ionic substance, such that the stoichiometric ratio it actually represents how that substance actually breaks down in an aqueous solution. So that's as far as determining the standard solution. So those are the steps that we took. We measured the amount of substance, weighted it in terms of mass, so that we can determine the moles of sodium hydroxide in that 5-gram sample. And we know the amount of water distilled water rather, that we used, in that volumetric flask to actually form that solution. So the solution is actually containing both the solute and the solvent particles, because this is essentially a homogeneous solution. Then if we say that this is a standard solution, we are saying that we know the concentration of this solution. We'll take a short break for now and look at more further examples. Let's take a short breather. Welcome back to our session. We're still talking calculations involving acid and base reactions in the context of titrations. We managed to see that this actually has a lot to do with stoichiometric calculations, and the calculations involved once a titration has been conducted would describe them as volumetric analysis. Now let's look at some of the important aspects in as far as a titration is concerned. Now, in terms of the terminology, so the technique involved is about the titration. So titration is about the technique, all right, of actually, using a standard solution. This is a technique or a procedure that is carried out using a standard solution to determine an unknown concentration. We spoke of an end point of a titration and a point of equivalence, where we spoke about the chemical indicators which have a color change, okay? So this has to do with the indicators, the end point, okay, where in a neutralization reaction, actually all the substances have actually reacted, right? And then what exactly are some of the apparatus or equipment actually involved in a titration? So what remains important is also for us to be able to identify the correct names of apparatus, or equipment that we use to actually carry out the technique or the procedure in a titration, which involves a reaction between an acid and a base. So identifying the apparatus is another skill that is very, very important, right? What are some of those? We know that there's a barrette which is actually calibrated to give us the volume of a solution that was used in a reaction. So this is the barrette. And then we also know of a beaker, okay, which will contain some substance which has been measured or pipetted. So the pipette actually measures a fixed volume of a solution, all right? And then at the end of the day, when a titration takes place, we know actual volumes of substances or quantities. But remember, one of these solutions in this setup is actually a standard solution. So we'd use that standard solution to actually determine the unknown concentration of the other substance, right? Okay. Now, what exactly is involved in a titration? So before we actually start to titrate or carry out the whole procedure of a titration, we need to select an appropriate indicator, right? So you'd have mentioned, earlier on, the different indicators. So our choice of indicator in an acid-base reaction depends on the type of acid as well as type of what? base, which is also informed by the pH range in which that specific indicator actually undergoes a color change to show us the end point of this acid-base reaction, right? So we need to write down the colors of the indicators of the indicator in an acid and in a base, and then at the end point. So this is actually what is happening in as far as the choice of the indicator is concerned, right? Okay. Now we also need to measure out the exact volume, right? So this, I think this goes further to emphasize the measuring skill. For us to keep track of data in a chemical reaction, when we conduct a technique of titration, we need to be able to carry out measurements and record those volumes. Because remember, in the volumetric analysis, that involves the calculation, the maths part of it. We need those actual volumes to actually, so that we are able to quantify or to actually get the unknown concentration of the other substance, either the base or an acid. So in a nutshell, what we are saying is that if the acid is a standard solution, then the technique of titration would involve us determining the unknown concentration of the base, and vice versa. So if the base is also a standard solution, so in a titration, in that titration, we would actually want to determine the unknown concentration of the acid. Okay, the indicator, very, very important. It shows the color change at the end point of that acid-base reaction. So we also need to add a few drops of the indicator so that we can keep track of the color change in as far as the end point is concerned. Right. Okay, so we also have to fill the burette with the solution of the known concentration. Right. So what goes into the burette is actually the standard solution. Okay. Because this solution, we know its concentration. So the burette is actually calibrated, as you can see. It means that there are calibrations. So when it's completely filled, it will mark up to 0 mils, okay, whatever units are used. So as you allow that standard solution to come out of the burette so that it reacts with the base, it could be the acid or the base, it doesn't matter, and then you can keep measurements or track of how much of the standard solution in terms of volume has been used in the reaction, okay? And also, very, very important, you need to make sure that the bottom of the meniscus, so the meniscus is that curved, part of the liquid surface. So make sure that when you take readings, they're actually correct. And we also need to keep record of volume of solution in the burette, right? And also, we need to place the conical flask under the burette directly so that all the standard solution goes into that, actually the conical flask where there is the other substance. And then we add the solution in the burette and swirl gently. The swirling will actually ensure that at the end of the reaction, all the substances have reacted completely, okay? And then the color of the unknown solution will change in the region where the acid and the base mix, okay? So that's where the reaction actually takes place. And then the color would be at the point. We also take note that at the end point, there is that color change which will tell us that, okay, this reaction has reached, the end, and then we can take the readings in terms of the volume of the standard solution. So the pipette will be used actually to measure the volume of the solution that goes into the conical flask, right? Okay, so we need to also keep track of the color change. We've mentioned that, right? So as we approach that, end point, we need to release drop by drop, just in small amounts so that we also address the issue of accuracy in terms of the volume of the standard solution, okay? Right, and then also we need to record the volume of the solution in the burette, that's of the standard solution, okay? And the volume of that of the other substance would have been recorded, the one that goes into the conical flask, okay? So it's about, measurement, and more measurement, right? So at the end point, we would actually say, okay, so this is roughly the amount or the volume of the standard solution that was used in the titration. Okay, then we would obviously have to repeat the procedure, more than once, say 3 times, because just to get a sense, the first one is basically to give us a rough estimate in terms of how much volume of standard solution is actually used. So if we repeat the procedure 3 times and average, that also appeals to, the accuracy of our results. So in any experiment, if we do 3 trials and average, we get a better sense in terms of the actual or the most accurate readings in as far as the data that we collected, right? So if you repeat that, that's one way of improving accuracy. So these are some of the most important aspects in as far as the actual technique or the procedure of a titration. After the short break, we'll try and look at tangible example, practical examples of a titration, as well as the calculations in as far as the volumetric analysis. Let's take a short break for now. Welcome back. We've managed to look at exactly what happens in the entire procedure in as far as the titration is concerned. Now that we've would have collected the data, then how then do we use this data in terms of the volume of the standard solution, what happened at the end point in terms of the color change. Now we have to do the calculations, because remember, our initial objective in terms of the titration was to use a standard solution to determine the unknown concentration. Let's see how that kind of works out, once we have done the titration. So the key term now that focuses on this segment is actually on volumetric analysis, which is basically about the calculations, okay? These are actually stoichiometric calculations of the data in terms of the volume of the standard solution, volume of the solution of unknown concentration. But at the end of the day, this has to do with us determining the unknown concentration, okay? So we're determining the unknown concentration by use of a standard solution, right? Okay. Now, in as far as volumetric analysis is concerned, what is it that we require to carry out the calculations of determining the unknown concentration using a standard solution? Okay, the known concentration of the acid or the base. So C subscript A represents the concentration of acid, and then C subscript B represents the concentration of the base. So for us to do volumetric analysis, to carry out volumetric analysis calculations, one of these two must be known, and would describe that as a standard solution. Okay, what else do we need? We also need the exact volume of the solution of the known concentration. This is our standard solution from the titration, the one that came off from the pipette, okay, and then we recorded that value. It's either the volume of acid or the volume of the base, right? And then again, what do we need? We need the exact volume of the unknown concentration, the one that we pipetted. So it's either volume of acid or volume of base. It can be one of the two. And then again, very, very important, when it comes to the law of conservation of matter, we know that these substances, they actually react in fixed ratios, and we talk about the mole as the SI unit of quantity of matter. So the balanced equation of reaction actually gives us the stoichiometric ratio in which these substances actually react with each other, okay? So we also need the mole ratio of the acid base from the balanced equation of reaction, right? Okay, then the volumetric equation comes actually from the formula, concentration of a substance is moles of substance per unit volume, which gives us moles of whatever, be it an acid or base, is equals to actually the product of the concentration and volume. So this is the actual ratio of the substances in terms of the acid and the base. So this would come from the balanced equation of reaction, okay? So the whole issues of, chemical formula come into play. Sometimes the equation is already balanced, given to you. In other cases, you need to carry out the balancing. So this is the balanced equation of reaction. So this is actually the stoichiometric ratio in terms of, the moles of the acids as well as the base, right? Okay. Now, when it comes to the calculations, let's go through the steps that one needs to take in as far as the volumetric analysis is concerned. It says here, in a titration, as an example, that volume, which is 30 cubic centimeters of sulfuric acid. So this is our acid, okay? One thing for sure, we must go back to chemical formula. This is H2SO4. It's an aqueous solution. So the correct chemical formula will have a lot of implications in as far as the balanced equation. So if the formula is incorrect, then it means it will affect also how we balance that equation of reaction. So this volume of sulfuric acid is neutralized, okay? Once it says neutralized, we immediately, remember, oh, okay, it is about an acid-base type of a reaction. Hence, we describe it as a neutralization type of a reaction, okay? So there is 40 cubic centimeters of sodium hydroxide. This is our base, right? So sodium hydroxide, chemical formula, NaOH, okay? That's a homogeneous solution, okay? And then whose concentration is that? All right. Now, calculate the concentration of the acid. Now, one thing that stands out from the onset is that the concentration of the base is given. In other words, what does that imply? It says to us that this base is actually our standard solution. Then our intention from then on is to try and use this known concentration to determine the unknown concentration of the acid. That's what becomes clear from the onset. Right, and then it says, step number 1, write down the balanced equation of reaction. So it's an acid-base reaction. What do we have? We've got sulfuric acid, which is H2SO4, okay, plus the base, which is sodium hydroxide, Na, okay, OH, This gives us a salt. Okay, our salt will be sodium sulfate, right? Remember, sodium is a group 1 metal, and then the sulfate ion is a polyatomic ion, SO4 2 minus. And then the formula for sodium sulfate then becomes Na2SO4, right? So we've got Na2, okay, SO4, okay, and then plus water, all right. Is the equation balanced? Let's check. Already we see that there is 1 atom of sodium on the left and 2. It means here we need to put a 2, right? If we do that, then we ask ourselves, is hydrogen balanced? Hydrogen, what do we have? We've got 4 hydrogen, okay? And then on the left, and then on the right, we only have 2. So it means we need a 2 there, right? Let's check the oxygen. Oxygen that we have, it's 4 plus 2, which gives us 6. We've got 4 plus 2. Now the equation is actually balanced. So what does this tell us? It tells us that the stoichiometric ratio is 1:2, the acid-base ratio. This is what we are particularly interested in, right? Okay. Now the balanced equation of reaction then becomes H2, okay, SO4, that's the sulfuric acid, okay, plus 2 moles of sodium hydroxide, which is our standard solution, which is a base in this case. Then we've got Na2, the salt, sulfate, okay, plus 2H2O, right? Now, what is our stoichiometric ratio? It's 1:2. Okay, so this is the balanced equation, right? Furthermore, and then number 2, we want to identify the variables. The variables are actually the quantities that we would need to use in our volumetric analysis equation in terms of concentration, volume, and moles of substance, right? So what do we have here? We already have the volume of sulfuric acid. So volume of acid, if we can quickly do the conversion to SI unit, because we know concentration is in moles per cubic decimeter. So 30 cubic centimeters, which is the volume of acid, is same as 0.03 cubic decimeters. So we divided that by 1,000. But where does that come from? 1 cubic decimeter is equals to 1,000 cubic centimeters, right? Right. And then what else do we have? We also have volume of base. Okay, volume of base is equals to, what do we have? 0.04, okay, cubic decimeters. What else do we have? We also have the concentration of the base, right? So C of the base is equals to 0.2 moles per cubic decimeter, right? These are the quantities that we can immediately pick up from, the story that is given to us. Very, very important, right? And then once we've done that, we are able to move to the next step, which is to determine the stoichiometric ratio. So the stoichiometric ratio actually comes from the balanced equation of the reaction. What are we saying? We are saying that the ratio is 1:2, right? So the stoichiometric ratio of the acid to base, in this reaction is 1:2. What does this mean? It means that a mole of the acid reacts with double the number of moles of the base. This is the fixed ratio in which these substances actually react with each other. So we're mainly concerned about the reactants in this case, right? Okay, now step 4, we must use the formula to complete the calculation. Okay, what does the formula say? The formula says to us moles of acid over moles of base is equals to concentration of acid, volume of acid, divided by concentration of base, volume of base, right? So this is what we have. Now, the stoichiometric ratio of acid to base is 1:2, right? Is equals to, we don't know the concentration of the acid because the question says calculate the concentration of the acid. In other words, we're looking for C subscript A, right? So this is the unknown, okay? The volume of acid that we used is equals to 0.03 cubic decimeters, okay? And then the concentration of the base, which is a standard solution in this case, is 0.2, right? Okay, and then the volume that was used is 0.04, right? So if you look at the substitution, so first is the correct formula that we copied without trying to manipulate it, and then we did the correct substitution with the necessary conversion of units, and then we can be able to isolate our unknown, which is the concentration of acid. So the concentration of acid in this case, if we cross multiply that, actually it will give us something like Ca is equals to 0.2 multiplied by 0.04, okay? If you multiply that by 1, it won't change anything. And then we have to divide by, 2 multiplied by 0.2 multiplied by 0.3 actually, just to correct that, okay? Right, so the substitution is very, very important in the sense that because the data is given, so if we make that the subject, it will be 2 multiplied by 0.03. That's our substitution there. So then we've got our concentration of the acid. So to determine that, would then say, from the calculator, what do we have? We have 0.2 multiplied by 0.04, okay? Multiplied by 1, okay? We can put it because the marks are given for substitution. Then at the denominator, we've got 2 multiplied by 0.03, right? Okay, what does that give us? It gives us the unknown concentration of the acid, which is 0.13 moles per cubic decimeter, okay? 0.13 mole per cubic decimeter. So that's exactly how we determine the unknown concentration, right? Then maybe a different example altogether, because now we know all the steps. There's a reaction between sodium hydroxide, which is used to, neutralize ethanoic acid. So from the onset, we are given the mass of sodium hydroxide, okay? We also given the volume of the acid. So in this case, what do we have? We have a case of saying, okay, we've got sodium hydroxide, which is our base, okay? From the equation, it reacts with ethanoic acid. This is an organic acid, CH3COOH, okay, to give us what? Our salt, which is sodium ethanoate, CH3COONA, okay, plus H2O. Okay, that's our equation of reaction, right? So the ratio in which they react with each other, also very important. We need to realize that for every mole of a base, there is 1 mole of the ethanoic acid. So the ratio is actually 1:1. So if we go to the, the story, it tells us about the mass of sodium hydroxide, okay, in a volume. So we are able to determine the concentration of sodium hydroxide. So C of sodium hydroxide, okay, concentration of sodium hydroxide, we would calculate it by way of saying, okay, mass over molar mass times volume, which gives us the actual concentration. Then we've got 12.4 grams, okay, divided by 40, okay, 40 is the molar mass of sodium hydroxide, 300 in liters or in cubic decimeters, 0.3. So this is actually the concentration of sodium hydroxide, right? So once you get the concentration of sodium hydroxide, we are then able to use, the equation C, number of moles of acid, number of moles of base is equals to C of acid, volume of acid, divided by C of base, volume of base. So at the end of it all, what is different in this scenario is that we are able to determine this concentration of sodium hydroxide, whatever that is, and then this becomes our standard solution, right? So these are some of the, ideas that you need to actually, understand the steps that we went through in terms of determining the unknown concentration. They apply, universally to any scenario which involves a reaction between an acid and a base. So a lot of practice is very important in this section. For now, that's the time that we had to cover, calculations on titrations. For now, it's cheers and bye-bye.